Assalamualaikum. Hi everyone, welcome back. So we're going to continue with casting 4. So in the last class, we already see the overview of casting technology and heating and powering. So I hope all of you have already gone through the materials that I've posted and also the video. So we're going to continue with our lecture. Today we're going to continue with pouring molten metal and fluidity. So here is some engineering analysis on the pouring of the molten metal. Okay, so there are several relationships that govern the flow of the liquid metal through the gating system then into the mold. Okay, so one of the important relationship is called Bernoulli theorem. So Bernoulli theorem state that sum of the energy, which is heat, pressure, kinetic, and frictional at any 2 points in the flow liquid are equal. Okay, so this one can be written in the following form. So Bernoulli theorem is shown in this equation. So the first one is showing the point number 1 and this one is point number 2. So the component inside there will be H, which is the elevation of the point above a reference plane. P1 is the pressure at the point 1. This one is the density of the metal. This one is the gravity. Okay, so V1 squared is the velocity of the fluid flow speed at point 1, and then 2 over 2g plus F1. F1 is the head losses due to the friction, equal to H2. This one is the same things. The component is the same term, but this one is 4.2. This one is 4.1. So in Bernoulli theorem, the component shows that any value of this one, sum of all this one, this first point is equal to the sum of all the components in point 2. So now, Bernoulli equation can be simplified in several ways. For example, we can first, if we ignore the friction losses, so meaning that F1 and F2 equal to 0, and then we assume that the system remain at atmospheric pressure, which is P1 and P2 equal to PATM during the process. So P1 and P2 we can cancel out. So leaving the equation H1 plus V1 squared over 2G equal to H2 plus V2 squared over 2G. So now let us assume that this is the sprue, everything is coming inside the cavity, right? So for example, we assume that this is point 1 and this area at the length over here is P2. Okay, so if we take P2 as the reference point, so P2 will be, the height for the P2 will be 0, meaning H2, the height of the point 2 is 0. Okay, so then we can cancel the H2. Then if this P1 is taken as the point, okay, so this one will be the H value. So this one will be the H value to this one H. Okay, so during this point, during this time, the velocity of the molten metal is considered 0 because you just start pouring, right? So then V1 will be 0. So then we can conclude the equation become H1 equal to V2 squared over 2G. Okay, so then we're going to get the calculation for the velocity. So by simplifying this equation, you are going to get the V equal to 2GH square root. Okay, so that's how you simplify the Bernoulli theorem. Another relationship that we can see in the pouring of the molten metal is called law of continuity. So in continuity law, it states that the volume rate of flow remain constant throughout the liquid. So meaning that if Q is the volume flow rate, so and there is 2 points, so point 1 and point 2 will be equal in terms of the volume flow rate. So if we can express it, it will become Q equal to V1A1 equal to V2A2, where V1 is the velocity of the molten metal at the point, and A1 is the cross sectional area of that point 1, and V2 is the velocity of point 2 with the A2 as the cross sectional area of area 2. Okay, so if we want to put it together, so this one we will be able to calculate. Let's say if you want to know the velocity of V1 while V2 you already know, then you can calculate the V1 using this equation. Now, if we assume that the runner from the sprue base to the mole cavity is horizontal, like in this picture, so let's say the runner to the cavity, this area is horizontal, so point 1 and point 2 is the same height, so there is no h value over here. So due to this, we assume the volume rate of flow through the gate into the mole cavity will remain equal to V times A. Okay, so at the base here. So accordingly, we can estimate the time required to fill the mole cavity by using this equation, TMF, which is time for mole filling, equal to V over Q. V is the volume of the mole cavity, so this is the mole cavity, and Q is the volume flow rate. So the summary for the formula that we already seen from Bernoulli theorem and also law of continuity, velocity can be calculated by using the first equation. Second one, volume flow rate using the law of continuity, and assuming from the law of continuity, we can get the time required to fill the mole cavity by using the V over Q. Now let us see the example on how to use this equation. For example, a mole sprue is 20 cm long and cross-sectional area at the base equal to 2.5 cm squared. The sprue feed a horizontal runner leading into a mole cavity whose volume equal to 1560 cm cube. So determine A. Velocity of the molten metal at the base of the sprue, B. Volume rate of the flow, and C. Time to fill the mole. So let us look into A first. So the velocity of the flowing metal V equal to V equal to square root of 2gh. Okay, so here 2 is already there. G is 981, and then the mole sprue is 20 cm long. So the sprue from the top to the base is 20 cm. So you put it here 20, so you'll get 198.1 cm per second. Now volumetric flow rate Q equal to, if you can remember, Q equal to VA, right? So volumetric flow rate can be calculated by using this equation. So the base, the cross-sectional area is 2.5 cm cube. So it's supposed to be this one is A, this one is V. So when you calculate, you will get this value. Time required to fill a mole cavity is TMF equal to V over Q. So Q we already have. V is given here 1560 cm cube. So this one 1560 over 495 cm cube over second. So then you will get the time to fill in the cavity is 3.2 seconds. Here is another example. So you can use the same method like previously explained. The equation also the same. So you can try and see whether you can solve the problem. So the molten metal flow characteristic often described by the term fluidity. So it's a measure of the capability of the metal to flow into and fill the mold before it starts freezing. So the property of flowing easily inverse of viscosity. As viscosity increase, fluidity will decrease. Here are the parameters that affect the fluidity. One is powering temperature. Uh, relative is relative to the melting point. Uh, and then metal composition, whether it's a pure metal or eutectic or alloy. So, and heat of fusion of each material, it will be different. So then it can affect the fluidity, viscosity of the liquid metal itself, and then heat transfer to the surrounding. So fluidity is desired during casting up to certain range. But if molten metal is over fluidity, it can cause disadvantages to the product and to the operation. First, it can cause oxide formation to the product that we produce if the pouring temperature is too high. And then it can also create gas porosity because the temperature is too high. When the temperature of the molten metal is too high, then when it react with the moist sand, it can create the water evaporation, and then it will cause the gas porosity, and then it can also penetrate into the sand. So then there will be in the space between the sand and also the metal will be eroded. Okay, so there will be penetration of liquid, so then you will not get the right product at the end. Due to that, usually the fluidity is measured. So measurement of the fluidity can be made using the spiral mold test. So which fluidity is measured as the length of the spiral channel that is filled by the molten metal prior to solidification. There are certain limit where the fluid can go up to, and then if it is go beyond that limit of place, beyond that limit, so meaning that it is over fluidity. So that's the end of casting 4. See you in casting 5.